Hello students, welcome to EPG Pathshala. I am Dr. Aditya Saxena from Department of Physics, Central University of Haryana. Today, we are going to discuss about the module Conservation Laws 1 from the paper Electromagnetic Theory. In this module, the students will get to know about the following: the alternative method of writing the energy in the electrostatic case in terms of the field rather than the charges is explained. Exactly in the same fashion, it is explained as to how the energy in a current loop can be thought of as being stored in the magnetic field. The general case of electrodynamics involving changing electromagnetic fields is taken up and the law of conservation of energy is derived. Again, in this and the next module, we look at the various classical conservation laws for a system of charges and the electromagnetic fields. We will see that for a proper understanding of the laws of conservation of energy, momentum and angular momentum, etc., we must endow the electromagnetic field itself with these attributes. Thus, the field becomes as real an entity as a particle carrying its own energy and momentum. In this module, we will look at the law of conservation of energy, known in this context as the Poynting's theorem, and study momentum and angular momentum conservation. In the next module, we begin by looking at some of the well-known results from electrostatics and steady currents and recast them in a form which is more useful for our present studies. Energy in electrostatic field. Now let us look at how we can develop a proper understanding of the laws of conservation of energy and momentum, etc. in case of the electromagnetic fields. And for this, let us now first look at how we can calculate the energy in the electrostatic field. We may write the expression for the energy in electrostatic field in many different ways, with which you are already familiar. So one of the very familiar expressions in which we can express the energy of the electrostatic field is that W, which also represents the work done, is equal to 1 upon 8 pi times epsilon naught whole into summation over I and j going from 1 to n, where I is not equal to j and I and j are indices, and this summation over the expression q and then I qj upon modulus of vector x subscript I minus vector x subscript j, where these subscripts or indices I and j represent two different charged particles whose charges are represented by qi and qj, while their respective position vectors with respect to a common origin are represented by the position vectors vector x subscript I and vector x subscript j. Here, the reason why we've written 1 upon 8 pi epsilon naught is to ensure that we do not go over the summation twice. Another way of writing this expression is if we convert the into charge densities. So in case if we, instead of having point charges, if we have charge densities which are confined in a volume, then we can write the same work done or the energy of the electrostatic field as given by 1 upon 8 pi times epsilon naught whole into double integration with one integration over the volume is over the charge density rho as a function of position vector x and the volume element d cube x, and the other is over the charge density rho as a function of position vector x prime over the volume d cube x prime over modulus of position vector x minus position vector x prime. Now we can further modify this relation that we have written for the charge densities by using the definition of the electric potential in case of the electrostatic fields. And using this definition, we know that the electric potential, if you solve the Poisson's equation, which is basically Laplacian operator acting on the electric potential, and that gives us minus of the charge density upon epsilon naught. So using that definition of the electric potential and solving that Poisson's equation, the expression for the electric potential that we get is what is also contained in this expression that we have written for the energy of the electrostatic field. So if we use the charge density as a function of the position vector x prime integrated over the volume d cube x prime over modulus of position vector x minus position vector x prime, then this is what we know is the expression for the electrostatic potential. So the modified equation for the electrostatic energy can then be written as W is equal to half integration over the volume element d cube x running over charge density rho as a function of position vector x times the electric potential phi as a function of position vector x. Now, if you look at all these three expressions that we've just discussed, then all these expressions involve the position of the charge. And there is an emphasis on the fact that the energy arises from the Coulomb's force, because if you look at the third expression, then you see that you're using actually the Coulomb's electrostatic potential, while if you look at the first two expressions, then you use the Coulomb's force equation for finding out the energy of the electrostatic field. So the alternative way is to express the energy in terms of the electric field. And for doing this, we again use the Coulomb's law, which is also the first of the Maxwell's equations and also referred to as the Gauss's law of electrostatics, which can be expressed as the divergence of the electric field is equal to rho upon epsilon naught, where rho is the charge density. And using this definition of the divergence of the electric field, we will eliminate in the last of the three expressions of the energy in the electrostatic field the quantity that is the charge density rho. So if we replace the rho occurring in the third expression with this Coulomb's law, then the expression for the energy in the electrostatic field gets modified to W is equal to epsilon naught by 2 integral over the volume element d cube x running over divergence of the electric field times the electric potential phi as a function of position vector x. And this expression can then further be written as epsilon naught by 2 whole times volume integral over the volume element d cube x running over bracket open divergence of bracket open the electric potential times the electric field bracket close minus the electric field dot the gradient of the electric potential, that is the scalar product of the electric field and the gradient of the electric potential. Now here we can use the Gauss's theorem to convert the first integral into a surface integral, because we know that using the Gauss's theorem, if we have the divergence of a vector quantity in a volume integral, then it can be converted into a surface integral. So doing that, we get a surface integral which goes to 0 for fields that fall off sufficiently rapidly. That is the first term on the right hand side. If it is converted into a surface integral using the Gauss's theorem, then for fields that fall off sufficiently rapidly with the position vector, this integral goes to 0. So basically what we are left with is only the second term in the integral, and then we can use the definition of the electric field in terms of the electric potential as defined in electrostatics, which is the electric field is negative of the gradient of the electric potential, and then we get the expression for the energy in the electrostatic field as W is equal to epsilon naught by 2 volume integral over the volume element d cube x running over E square, where E is the electric field. And this can be then written as volume integral over volume element d cube x running over W subscript electric as a function of position vector x, where W subscript electric as a function of position vector x is epsilon naught by 2 whole times the square of the electric field. Now we can express the energy of the electrostatic field in terms of the electric field rather than in terms of the Coulomb's force as was done initially. And here instead of using the charge or the charge density, the term that we use is the energy density, which is given by W subscript electric as a function of position vector x at the point given by or denoted by the position vector x. So this definition of the energy of the electrostatic field provides an alternative interpretation, that is, the energy resides in the field rather than the charges. Although in electrostatics this change in the interpretation does not matter much, but where it becomes very significant is the fact when we have time varying electric and magnetic fields. And here the second interpretation is much more important, significant, and natural. Energy in magnetic field. Now let us try and calculate the energy in magnetic fields. So now let us consider a single circuit with a constant current I that is flowing through it. Now we all know that whenever there is a change in the flux in the circuit, it will induce an electromotive force epsilon, which is the consequence of the Faraday's law of electromagnetic induction. So if we want to calculate the work done on a unit charge against this induced electromotive force, then this is minus of epsilon. So the total work done per unit time can then be given as differentiation with respect to time of the total work done W is equal to minus epsilon times I, where epsilon is the electromotive force, the induced electromotive force, and I is the current which is flowing in the circuit. Now if L is the self-inductance of the coil, then this induced electromotive force can be written as, in terms of the self-inductance L of the coil, as epsilon is equal to minus of L times differentiation with respect to time of the current I that is flowing in the circuit. So the expression for the total work done per unit time, that is differentiation with respect to time of the total work done W, is equal to L times I times differentiation with respect to time of the current I, where L is the self-inductance of the coil and I is the current that is flowing in the coil. So if we want to find out the total work done in building up the current from 0 to its present value I, then we integrate the above expression with respect to time, and that finally yields the result that the work done W, that is the total work done, is equal to half times the self-inductance of the coil L times the square of the current flowing in the coil, that is I square. Now using the Stokes theorem, we know that the flux of the magnetic field through this current loop is given by phi is equal to surface integral over the element area dA, that is the magnetic field induction vector B dot dA vector. And then using the Stokes theorem, we can convert this surface integral into a line integral. But before we do that, what we will do is that we will use the definition of the magnetic field induction vector in terms of the vector potential. So if A vector is the vector potential, then the magnetic field induction vector B can be written as the curl of the vector potential A. So using this expression, the expression for the flux through the loop, that is phi, becomes equal to surface integral over the surface element area dA running over the curl of the vector potential A dot dA. And this, when we use the Stokes theorem to convert it into a line integral, gives us the value, the line integral over the closed loop running over the vector potential A dot the line element vector dl. Energy in magnetic field. So once we have defined the flux for the loop through which a current I is passing, then this flux, using the definition of self-inductance, we see is equal to Li. That means that phi is equal to L times I, where L is the self-inductance of the coil and I is the current flowing in the coil. So equating these two expressions of the flux associated with the current loop, we can get the result. The self-inductance L times the current I is equal to line integral over the closed current loop running over the vector potential A dot the line element vector dl. And using this definition, we can then substitute this definition in the definition that we've defined above for the work done or the energy in the magnetic field that is stored in the magnetic field. So we can replace the value of the self-inductance times the current with the expression that we obtained in terms of the vector potential. And using this substitution, we can then finally write down the value of the total work done as given by W is equal to half times volume integral over the volume element d cube x running over the vector potential A dot the current density J, where the dot represents the scalar or the dot product between the vector potential A and the current density J. And here we have used the definition of the current density, which if we want to write in terms of the current, so the current can be written as the current density, the integration over the current density with the integration running over the surface with the surface element dA. Now let us use the Ampere's law to eliminate the current in favor of the magnetic field, so that the expression for the work done that we've obtained above then gets modified to W is equal to 1 upon 2 mu naught times volume integral over the volume element d cube x running over the vector potential A dot within brackets the curl of the magnetic field induction vector B. And since this expression within the bracket involves a scalar triple product between the vector potential, the del operator and the magnetic field induction vector, so we can then expand this to get the result, and this is equal to 1 upon 2 times mu naught whole times volume integral running over the volume element d cube x bracket open the magnetic field induction vector B dot within brackets curl of the vector potential A minus the divergence of the cross product of the vector potential A and the magnetic field induction vector B bracket close. Now in this above expression, we use the Gauss's divergence theorem on the second term on the right hand side of the expression to convert it into a surface integral from the present volume integral. And again, by the same arguments that we had used above, that this surface integral vanishes on infinitely large surface for the magnetic fields that fall off sufficiently rapidly. Further, we use the definition of the magnetic field induction vector B in terms of the vector potential A, which is given as vector B is equal to the curl of the vector potential A. And substituting that in the above expression, we finally get the result of the total work done, or rather by the magnetic field, as W is equal to 1 upon twice mu naught times volume integral over the volume element d cube x over square of the magnetic field induction vector B. And this can then be written as volume integral over the volume element d cube x running over the energy density, which is denoted by W subscript magnetic as a function of position vector x, where this energy density due to the magnetic field, that is W subscript magnetic as a function of position vector x, is equal to 1 upon twice mu naught whole times the square of the magnetic field induction vector B. And in the same manner as we had done above for the electric field, similarly over here we have been able to provide an alternative interpretation for the magnetic field energy. Conservation of energy in electromagnetic field. after having discussed individually the cases of the energy stored in a magnetic field, now let us come on to the general case of the time-varying electromagnetic fields. So if we have a charge q which is moving with a velocity vector v, then the rate of work done on this charge is given by using the definition of the Lorentz force. So the time derivative of the work done on this charge is equal to the force F, that is the Lorentz force, dot time derivative of the displacement, that is the scalar product of the Lorentz force and the velocity vector v. Now using the definition of the Lorentz force over here, for a charged particle q which is moving in both the electric and the magnetic fields is given by, so time derivative of the work done w is equal to charge q times bracket open the electric field vector E plus the velocity vector v cross the magnetic field induction vector B whole bracket close dot product with the velocity vector v. Now in this expression, if we look at the second term, then if we do a cyclical rotation of the terms, because it's a scalar triple product, we see that in one of the terms we will have the term v cross v, that is the velocity vector will be in a cross product with itself. And since we know that any vector in cross product with itself gives 0, therefore we only are left with the first term in this expression. So the time derivative of the work done is equal to the charge q times the dot or the scalar product of the velocity vector v and the electric field E. Then using the definition of a continuous distribution, that means replacing the charge and the velocity vector with the current density vector, we can rewrite the expression of the time derivative of the work done as equal to the volume integral over the volume element d cube x running over the current density vector j dot the electric field vector E, that is the scalar product of the current density vector and the electric field vector. Now this expression for the rate of work done, which is actually equal to the power, represents a conversion of the electromagnetic energy into the heat or mechanical work done on the charged particles. So if the total energy of the system is to remain constant, then this change or conversion must be compensated by an equal rate of decrease of the electromagnetic energy within the volume V. And in order to exhibit this conservation law explicitly, the right hand side must be written in terms of the field alone. So now what we do is that we use the Maxwell's second equation, which gives us the curl of the magnetic field induction vector B is equal to mu naught times the current density vector J plus mu naught times epsilon naught times the partial derivative with respect to time of the electric field E. And we use this definition, or rather this Maxwell's equation, to eliminate the current density vector J from the above expression for the work done or the power. Conservation of energy in electromagnetic field. Now once we use the Maxwell's equation to eliminate the current density vector J from the equation of the power on the right hand side, and we also make use of the Faraday's law of electromagnetic induction, then what we have is the vector identity, which is given by the divergence of the cross product of the electric field vector and the magnetic field induction vector. And this vector identity can be written as the scalar or the dot product of the magnetic field induction vector with the curl of the electric field vector minus the scalar or the dot product of the electric field vector with the curl of the magnetic field induction vector. So using the Faraday's law, which is basically del cross E is equal to minus del B by del T. So using that law and this vector identity and replacing this in the above equation for the power and eliminating the value of the current density J, we finally get the conservation law in the form volume integral over the volume element d cube x the scalar or the dot product of the current density vector J and the electric field E is equal to minus of the volume integral over the volume element d cube x running over bracket open 1 upon mu naught times the divergence cross product of the electric field vector and the magnetic field induction vector plus 1 upon mu naught times the magnetic field induction vector dot the partial time derivative with respect to the magnetic field induction vector plus epsilon naught times the scalar product of the electric field vector with the partial derivative of the electric field with respect to time. So here, if we look at the second expression on the right hand side, then this expression can be written as epsilon naught by 2 times E square, where E is the electric field, and this gives the energy density in the electric field, while the second term on the right hand side of the above expression gives 1 upon twice mu naught times the square of the magnetic field induction vector B, which is the energy density in the magnetic field. And the sum of these two quantities, that is 1 upon 2 whole times bracket open epsilon naught times the square of the electric field plus 1 by mu naught times the square of the magnetic field induction vector B whole bracket close, represents the total energy density in the electromagnetic field even for the time varying case. So using these expressions in the above equation, we finally can write down the expression for the energy density as given by minus of volume integral over the volume element d cube x running over the scalar or the dot product of the current density J and the electric field E is equal to volume integral running over the volume element d cube x over bracket open del U by del T, where U is representing the total energy density in the electromagnetic field and is given by half times bracket open epsilon naught times E square plus 1 upon mu naught times B square bracket close. So partial derivative with respect to time of this energy density U plus 1 upon mu naught times the divergence of the cross product of the electric field and the magnetic field induction vector whole bracket close. Poynting's theorem. Again, we use the Gauss's theorem to convert the volume integral to a surface integral over the bounding surface. This gives the result minus of the volume integral over the volume element d cube x going over the dot product of the current density J and the electric field E, and this is equal to the volume integral over the volume element d cube x over the partial derivative with respect to time of the energy density U plus 1 upon mu naught times surface integral over the bounded surface, the cross product of the electric field vector E and the magnetic field induction vector B with the dot product with the surface area element vector dA. This is the Poynting's theorem. The first integral on the right is the total energy stored in the electromagnetic field, while the second term on the right is the rate at which the total energy is carried out across the bounding surface. Poynting's theorem then says that the negative of the rate of work done by the charges is equal to the rate at which the energy increases inside the volume plus the rate at which the energy flows out of the volume. The energy per unit area per unit time transported by the fields is called the Poynting's vector and is given by the vector S is equal to the cross product of the electric field and the magnetic field induction vector B divided by mu naught, and this is equal to the cross product of the electric field and the magnetic field. Conservation law rewritten. So the Poynting's theorem is finally written as minus of the volume integral with respect to the volume element d cube x running over the scalar or the dot product of the current density J and the electric field vector E, and this is equal to the volume integral running over the volume element d cube x over the partial time derivative with respect to u, that is the energy density of the electromagnetic field, plus the surface integral of the Poynting's vector s dot the surface area vector dA, where the scalar or the dot product of the Poynting's vector s and the surface area vector dA is the energy crossing an infinitesimal area element dA vector per unit time, or the energy flux, and the Poynting's vector s is also called the energy flux density. So we can then rewrite the second term on the right hand side of the above equation by using the Gauss's theorem and convert the surface integral into a volume integral. Then we get the differential form of the above equation, which can be written as partial time derivative with respect to the energy density of the electromagnetic fields, that is u, plus the divergence of the Poynting's vector s is equal to minus of the scalar or the dot product of the current density vector j and the electric field E. And as we can see from the form of this equation, that this equation is a continuity equation. Further, the work W done on the charge system increases its energy, and this increase in the energy appears in the form of heat or mechanical energy. And this energy shows up as the increase of energy of charged particles per unit volume. So, in that sense, what we can conclude is that the Poynting's theorem is then a statement of the conservation of energy of the combined system of charges and fields. Conservation law for charges and fields. So now if we denote the total energy of the particles within the volume V by the term W subscript mechanical and assume that no particles move out of the volume, then we can write down as the rate of this mechanical work done, time derivative of W subscript mechanical is equal to volume integral over the volume element d cube x of the scalar or the dot product of the current density vector j and the electric field E. So using this definition of the rate of mechanical work done, we can then write down the rate of total work done as the derivative with respect to time of the total work done W is equal to derivative with respect to time of the work done subscript mechanical plus the work done by the fields denoted by the term W subscript field, and this is equal to minus of the surface integral running over the surface area element dA over the surface area vector n dot the Poynting's vector s. And then using Gauss's divergence theorem, the surface integral can be converted into a volume integral and can be written as minus of the volume integral over the volume element d cube x over the divergence of the Poynting's vector s. So in this sense, the Poynting's theorem expresses the conservation of energy of the combined system. That is, if U subscript mechanical is the mechanical energy density, the above equation takes the form derivative with respect to time of the volume integral over the volume element d cube x of the total energy density U is equal to the derivative with respect to time over the volume integral over the volume element d cube x over bracket open the energy density due to mechanical, that is U subscript mechanical, plus the energy density contained in the fields or due to the fields, that is U subscript field, and this is equal to minus of the volume integral over the volume element d cube x over the divergence of the Poynting's vector s. And then we can write down the same equation in the differential form, which can then be called as the differential form of the Poynting's theorem, and this is that the partial time derivative of the total energy U is equal to the partial time derivative of bracket open the mechanical energy density U subscript mechanical plus the energy density due to the electromagnetic fields, that is U subscript field, bracket close, and this is equal to minus of the divergence of the Poynting's vector S. So students, now let us summarize what all we have learnt in this module. Firstly, we learned an alternative method of writing the energy in the electrostatic case in terms of the field rather than the charges. Next, exactly in the same fashion, we explained or rather got to know as to how the energy in a current loop can be thought of as being stored in the magnetic field. Then we discussed the general case of electrodynamics involving changing electromagnetic fields, and this is taken up, and the law of conservation of energy called the Poynting's theorem was derived, wherein we also saw that actually the energy is contained in the fields, in the electromagnetic fields. It is explained that for a proper understanding of the law of conservation at a local level, it is essential that the energy be assigned to the electromagnetic field. Thank you.